Hello Chem 1A, this is Chapter 5, Lecture Video 3, and we're going to be talking about solutions and their concentrations more specifically here. So we've already kind of talked about solutions a little bit in Chapter 4. They're composed of a solute and a solvent. We have two ways of describing how much solute is present in a solution, right? And that's the qualitative method, saying things like, it's a concentrated solution. This means there's a lot of solute present in my solution. Or it's a dilute solution. There's not much solute present then in a dilute solution. There's also a quantitative method of talking about how much solute is present in our solution, and these are concentrations. Concentrations typically specify the amount of solute and solvent present in a solution. Now, the biggest concentration unit that we use in chemistry is known as molarity, and molarity is defined as the moles of solute per liter of the solution. And the solution, volume of the solution, or liter of the solution, is going to contain both the volume of the solute and the volume of the solvent in the solution. So if we're calculating the molarity of, let's say, compound X, then we would say moles of the solute is in the numerator, liters of the solution are in the denominator, and we simply divide. The units are moles per liter, but often we use a symbol to represent this, which is known as the capital M, right? The capital M, that's molarity. Now, if I have concentration of NaCl is 1.00 moles per liter, this is totally fine to write it that way. I kind of prefer it that way personally because it shows you all the units, but most often you're going to see it like this because honestly, chemists are lazy. We don't like to write. So we would probably write this as 1.00 capital M to indicate, hey, we're talking about molarity. And that means moles of NaCl, the solute, per liter of solution. Now, what do we use this for? Most often we use molarity to convert in between moles and volume. This adds a second dimension to our calculations in stoichiometry. So let's talk about ions. Like we talked about in Chapter 4, when we dissolve an ionic compound, because it's a strong electrolyte, it breaks apart into the ions that make it up. For instance, copper 2 chloride breaks apart into copper 2 plus ion and 2 Cl minus ions. Now, because of this, this actually affects the concentrations of either ion present in the solution, right? Because I don't really have a way of measuring how much of this solute and this solute are present in the solution because I added the solid and dissolved it in the water. I know how much solid I added because I can measure that. I can't directly measure the amount of ions present, but I can use mole ratios and really how many do they break apart into to figure out what their concentrations are as well. For instance, I know that for every 1 copper 2 chloride solution, I get 1 copper ion and 2 chloride ions present in solution. Let's say that I calculate a concentration of the ionic compound as 0.3 molar. Then my concentration of copper in the solution, copper 2 plus, is also 0.3 molar. The reason why? Well, in the reaction we have a 1-to-1 mole ratio between the copper 2 chloride ionic compound and the copper 2 plus ion. However, because we have a 1-to-2 mole ratio for chloride, the concentration of chloride present in the solution is 2 times that of the ionic compound, because for every 1 ionic compound I dissolve, I get 2 chloride ions, making its concentration 0.6 molar. So let's do an example problem. So let's say we dissolve 0.395 K2SO4 to give a total solution volume of 250 mils. What is the molarity of the K2SO4? Let's do that problem first, and then we'll get to the next two. Okay, so one of the first things we need to do if we want to calculate the concentration of K2SO4, we need two values, right? Moles over liters of solution. And this is moles of K2SO4, our solute. So if I want moles of K2SO4, I need the molar mass of it, and I need to get moles of it using the grams and the molar mass. So let's do that first. I know 3.95 grams of K2SO4 have been dissolved because I was given that value. I know that the molar mass of K2SO4, because I calculated it, is 174.27 grams of K2SO4 per mole of K2SO4. If we do this division out, we get the moles of K2SO4 is 0.002267 moles. Now, I'm going to leave it there. We should only have 3 sig figs, but we're doing a multi-step calculation. So this now goes there. Now we need to get volume of the solution. Well, we're actually given the volume of the solution, but there's a bit of a problem. It's in milliliters. We need to convert this to liters. So I know that 250.0 milliliters are present for the solution, and I know that in there are 1,000 milliliters in 1 liter. This gives me 0.2500 liters of solution. This guy now goes here, right? So my concentration of K2SO4 is equal to 0.002267 moles of K2SO4 divided by 0.2500 liters. Now, this one is actually only accurate to the 3rd sig fig, so when I divide this out, I get 0.00907 molar as my concentration of K2SO4 in the system. Now, because K2SO4, when dissolved, breaks apart into ions, it breaks apart into 2 K pluses and 1 SO42 minus, I can now get the concentrations of both K plus and SO4 2 minus, right? So because there's a 1 to 2 mole ratio between potassium sulfate and potassium, I know that the concentration of K plus is equal to 2 times the concentration of K2SO4, or in other words, 2 times 0.00907 molar, or 0.0181 molar. Now, because it's a 1-to-1 mole ratio for the sulfate, I know the concentration of sulfate ion here is just equal to the concentration of K2SO4. So my sulfate concentration then has to be equal to 0.00907 molar. All right, so if you have questions, let me know. Let's move on to the next topic here, dilutions. So when we say a solution is dilute, that's using it as an adjective. If we say I diluted a solution, I'm now using the word dilution or dilute as a verb. Now, when you do a dilution, when it's a verb, that's the action of adding more solvent to a solution. And the result of this is that we decrease our solute concentration. Let's look at why. If we look at this formula, concentration is equal to moles of solute over liters of solution. By adding solvent, I don't change moles of solute. Moles of solute stays the same, but I do change the total volume of the solution. If I increase the denominator, I'm going to decrease concentration, right? Now, that's why a dilution is going to decrease concentration, because we're increasing the denominator of our equation, thereby decreasing the numeric value of the concentration, because moles of solute is staying constant. Now, when this happens, this is very useful, because a lot of times we can't measure out a small enough amount of a substance to get the concentration we want, so we make a solution at a higher concentration, and then we add solvent until we get to the concentration we want. Now, there's a simple equation that can be used for this problem, and that is M1V1 is equal to M2V2, or M initial times V initial is equal to M final times V final. So let's do some calculations with that. What volume of 12 molar HCl is required to prepare a 100 milliliter solution of 1 molar HCl? Right, so this is V2, this is M2, and this is M1, and we're really being asked for what is V1, right? So if we look at that previous equation, M1 V1 is equal to M2 V2. We pretty much just can plug these values directly in. So 12 molar times V1 is equal to 1.0 molar times 100 milliliters. In this equation, it does not matter what unit of volume you use as long as you're consistent. So if I plug milliliters like I did in for V2 here, then V1 is going to come out in milliliters. So if we rearrange and solve for V1, we get that 8.3 milliliters of HCl at 12 molar is going to be required to do this problem, or to make this solution, I should say. So that's our answer. Let's do one more example here. Okay, what is the concentration of a solution prepared by diluting 25 milliliters of 14.8 molar nitric acid to a total volume of 1.5 liters? Again, we can use M1 V1 is equal to M2 V2. Now here, this is M1, this is V1, and this is V2, and what we're being asked to solve for is what is the new molarity, or in other words, M2. Now there's a slight issue. You might notice that our V2 is in liters and our V1 is in milliliters. It does not matter which direction you convert these two numbers, they just need to be in the same units. So I'm going to convert liters to milliliters. I know that 1.5 liters is 1500 milliliters. Now I'm going to put a bar here over this 0 to indicate that it does count as a significant figure. So let's plug in values and go from here. So 25.0 milliliters is my V1, and that's times 14.8, which is my M1, which is times M2, is equal to M2 times 1500 milliliters. So we can just rearrange and solve for M2 here. And what we get is 0.247 molar is my final concentration. All right, if you have any questions, please let me know.